Stanford University.
Hey everyone, thank you for having me here today. Again, my name is Debbie Senesky, and I'm coming from the Aeronautics and Astronautics Department. The name of my lab is the Extreme Environment Microsystems Laboratory, or the X-Lab. And the primary focus of my lab is to collect data in harsh or prohibitive environments. So environments such as deep space, the surface of Venus, or within combustion environments. But today I'm wearing my energy hat, and so I'll be talking about harsh environment sensors for smart power and propulsion systems. So recently there's been a push to improve our power and propulsion systems, such as industrial gas turbines inside of power plants, aircraft engines, and automotive engines, such that they reduce emissions, have increased efficiency, and also can operate on new types of fuels, so such as biofuels or combined fuels. And one way to improve these types of systems is to put sensors directly within the combustion environments found there. So for example, can you collect data about pressure, temperature, gas content, and feed that data back to control circuits so that we can tell, for example, our engine in our car to adjust the spark timing or the air-to-fuel ratio, again, improving that combustion process. So here's a picture, SEM image of a sensor and a circuit that is actually operated at 600 degrees C. Throughout this talk, I will tell you how you make these types of devices and why you would use them to improve our energy systems. This chart here is showing the energy flow, or the supply and demand within the United States. It's a little bit outdated, but I like this chart because it tells us why it's an exciting time to be an engineer. Right, so it tells us a little bit about the issues on the supply side. So for example, we're primarily reliant on our natural resources such as coal, natural gas, and petroleum. And so we need to increase the amount of energy we're produced by our renewable sources such as solar, biomass, wind, and hydropower. Right? In addition, on the demand side, what you can see here is that 50% of the energy is lost due to inefficiencies in the way we use our energy. Right? And so primarily I will talk about the power and propulsion system, so industrial gas turbines, light-duty vehicles, and aircraft engines. So can we improve the way we actually process our natural resources and make these systems more efficient? And so you can see there's a lot of work to be done in order to improve our supply and demand flow. California is taking the lead on some of these demands. For example, California is requiring or mandating that we be 33% renewable by 2020, and that we have a 25% reduction in carbon emissions by 2020, and then an 80% reduction in carbon emissions by 2050. So you can see there's a lot of work to be done in order to meet these targets. A lot of our energy systems have harsh environments within them. This is just a snapshot of some of the industry profiles that I look at in my laboratory. For example, subsurface systems found in geothermal and oil and gas wells, and also combustion systems, industrial gas turbines, automotive engines, and aircraft engines. And so I define a harsh environment as an environment that has extremes of pressure, temperature, shock, radiation, and chemical attack. And a lot of these systems have those types of environments within them, and also expose critical components to these environments as well. So we're talking temperatures between 300 and 600 degrees C. And so what if we were able to directly monitor the pressure, temperature, chemical content within these systems directly with sensors? That would enable us to provide real-time information about the subsurface environment, also the combustion process and critical components that are often prone to failure. And often, for example, in oil and gas exploration, these types of failures can be very, very bad for the environment. So one vision of the future is to co-locate sensors, integrated circuits, and energy harvesters in a wireless sensing module that can go directly within a combustion engine and collect the data. Again, the goal is energy efficiency and clean emissions. So in particular, there's a huge business case for industrial gas turbines. It costs $1 million to open up a gas turbine when it's prone to failure, right? So if one of these blades breaks, it costs $1 million to open this system up, right? So that's not very cost effective. Also, if we can improve the efficiency or the energy consumption of this device by 1%, we can reduce the carbon emissions by 400,000 tons per year per gas turbine. So very, very small gains in efficiency can prove large gains in emissions, which is great for the environment. So how do we do it today? This is an image of a gas turbine, and you can see this spaghetti soup instrumentation, right? So these are fiber optic devices which are used to look inside of the gas turbine, and this is a scheduled type of maintenance. This is scheduled. This is not done in real time, so you have to stop the system and then use your sensors, this spaghetti soup type of sensor system, in order to understand what's happening in the state of health of this component, and also to understand the actual process. So can we streamline this type of maintenance with small-scale sensor technology? In addition to industrial gas turbines, it's beneficial to collect data in subsurface environments. For example, well bores found in geothermal or renewable energy applications. And these well bores are around 2 to 5 miles deep within the earth, right? And for oil and gas exploration, it can be much, much deeper than that, some of the deep sea exploration. And so you can imagine it's critical to understand, number one, the health of these components, such as the cement, the wellbore, or the cement casing. In addition, it's helpful to understand this process. So in the geothermal example, can we understand what is the state of temperature or the state of pressure over the lifetime of the well? Are we still producing the same amount of energy that we expect? Similarly, for the oil and gas exploration, can we also prevent blowout deep within the ocean, for example? And also, can we understand the chemical concentration? And can we help to improve the way we navigate in subsurface environments? So how do we make some of the sensors that I'm talking about? The material platform that I've utilized over the last 8 years is called silicon carbide. It's a wide bandgap ceramic semiconductor material, so similar to the material you find in your cell phones or your laptop. It can be doped P-type or N-type by introducing particular atoms into its lattice. Today I will talk about some of the various polytypes of silicon carbide, 3C, 4H, and 6H. The 3 corresponds to the number of stacks in the stacking sequence, and the letter in the prefix corresponds to the crystallinity of the material. So C for cubic and H for hexagonal. And actually, silicon carbide is currently a platform material that is being developed for the power electronics industry, and so I'm piggybacking off this industry in order to make sensing devices. So why silicon carbide? This chart here is showing the material properties of silicon carbide in comparison to other wide bandgap semiconductors and also silicon. So silicon is the technology that is commonly used in your cell phones and your laptops. So what stands out to me when I'm trying to make harsh environment sensors is, number one, the sublimation point, so 28,000 degrees C, 2800 degrees C, sorry. So it takes a lot of energy to break apart the silicon and carbon bonds between the atoms in the silicon carbide. Also, it's a wide band gap material, around 3 eV, and so it takes a lot of energy to generate thermal carriers. Electrically, this material is very, very stable. In addition, its chemical stability is very, very superior to all of these materials. There are no wet chemicals that etch silicon carbide at room temperature. It has a very stable oxide layer, silicon dioxide. So you may be thinking, well, why not diamond? It has excellent mechanical and electrical properties. Diamond, when you expose it to hot oxidizing environment, it actually turns to graphite. So it's not suitable for environments such as a combustion environment, for example. And later on in this talk, I'll talk a little bit about gallium nitride and aluminum nitride, which are emerging materials, which are also wide bandgap, but they're also piezoelectric materials, which are interesting for sensor design. So coming back to silicon carbide, with my collaborators at UC Berkeley, or the other side of the bay before coming here, I've done some tests on the material properties. For example, we've tested the chemical resistance of silicon carbide. This is a silicon-based device coated with a very, very thin coating of silicon carbide, 40 nanometers. If we expose it to hot potassium hydroxide, an uncoated device completely disappears. A device with a very, very thin coating stays intact. So we can ruggedize some of our devices with very, very thin coatings of silicon carbide. In addition, we subjected it to wear. This is an uncoated silicon device. After 250,000 cycles of rubbing contact, you can see the uncoated device shows wear, whereas the silicon carbide coated device with a very, very thin coating, 40 nanometers, shows no wear. And silicon carbide is actually used to reinforce drill bits material, so it's a very robust material. In addition, the fracture strain is much, much higher than silicon, more than double at 3.3%. And its oxidation resistance is very superior to diamond. After exposing diamond-like carbon films to 100 hours in air at 850 degrees C, the diamond-like films completely disappear after 24 hours. The silicon films generate an oxide layer of around 300 nanometers. The silicon carbide films generate a very, very thin oxide layer of only 50 nanometers that terminates after a particular point. So again, this is just highlighting the superior chemical, mechanical, and wear resistance of silicon carbide. When we're talking about placing these components in geothermal wellbores, it's important to demonstrate that this material actually withstands supercritical environments. So in wellbores, there's supercritical water that actually cuts steel. So can this silicon carbide material survive in that type of environment? This is an image of a silicon die, again, the material you find in your laptops. After 20 hours of exposure to supercritical water, it erodes. The silicon carbide die before and after, you can see no measurable change in the mass of the silicon carbide. This plot here is showing the mass change over time. This is the red dots here showing silicon carbide, the percentage change in mass. No measurable change in the mass. The silicon shows 80% change in the mass over 20 hours of exposure. So can we use this material to make sensing devices? So at this point, we have to rethink our microfabrication processes. So silicon is 50 years in the making. We know how to make integrated circuits. We know how to make sensors that we put in our cell phones. Can we do the same thing with this silicon carbide material? And so one vision is to co-locate temperature, acceleration, pressure, and strain sensors all on a single chip. This is shown graphically here. Imagine the substrate, the electronics, the sensors, and the packaging are all made from silicon carbide. So there's a lot of work that needs to be done in order to realize this system. But this would be very, very useful, again, for some of these energy applications where we want to collect data in combustion environments, for example. This is an image of a low pressure chemical vapor deposition system that's used to deposit polycrystalline silicon carbide. We have these here over in the Stanford Nanofabrication Facility, and these are commercial-based systems that are also used in the semiconductor industry to deposit materials that would, again, be found in your cell phone or your laptops. This is an image of a thin film of silicon carbide that's conformally coated on silicon trenches. This can be done on 4-inch or 6-inch substrates. This is images showing released silicon carbide beams. So these were plasma etched beams of silicon carbide. The first image here on the top you're seeing is really curled beams. That's because once you release it from the substrate, there's intrinsic stress and they start to curl up. So you have to optimize your process in order to have stress-free films. And so you can see here, after some development, we were able to get stress-free films. So these are long flexures. This is about 1 millimeter in length after plasma etching, freestanding beams that can then be used to make sensing devices. This is a graphical image of a resonant strain sensor. So I'll tell you a little bit about how this device works. So strain sensors can again be used to tell you a little bit of information about the mechanical state of structures such as cement casing found in geothermal wellbores or oil and gas wellbores. And so this device is a double-ended tuning fork, so similar to a guitar string, you have these tines. As you stretch the tines, you get a change in frequency, similar to a guitar string. So as you put tension on your guitar string, you get a change in the sound, and that's because there's a change in resonance. And so you can drive these tines into resonance electrostatically with these comb fingers here. And you can also sense the change in the resonant frequency electrostatically with a secondary pair of electrostatic comb fingers. This is an image of a silicon carbide, polycrystalline silicon carbide strain sensor. The tines are shown here, and these are the electrostatic comb fingers that can then be used to, again, drive this device into resonance. As we apply a strain, the change in resonance occurs, and that can correlate to the level of strain in this sensing device. This is a cross-section of the fabrication process. Again, we use silicon substrates, polysilicon carbide thin films that are micromachined, and then we release this underlying sacrificial material to have these long released structures. So this is a hovering structure on top of a silicon substrate. So this device was subjected to temperatures as high as 600 degrees C. The backside of the sensor was irradiated with an IR lamp. It was driven with low temperature electronics at this point. We did this separately. We didn't have high electronics in order to interface with the sensor. But we used an IR lamp to heat this up to 600 degrees C. This is the temperature ramp here, the red dots going from room temperature up to 600 degrees C. And we can see the blue dots here denoting the frequency at which this sensing structure is resonating. What you can see here is once we hit 600 degrees C, the device continues to resonate. So this is a microscale device made of silicon carbide resonating at 600 degrees C. So a functioning electronic device at a very, very high temperature. Once it hits 600 degrees C, we turn on the dry steam, and it continues to resonate with no significant changes in the resonant frequency. So this is telling us that we can actually make functioning electronics at 600 degrees C in hot oxidizing environments, similar that you would find in combustion environments, for example. So what about metallization? In addition to your sensors, you have to have the packaging, the electronics to go along with it. This is an image of a test structure used to study high temperature metallization on silicon carbide. Our first thinking is to use platinum because it's a high temperature metal. It's an inert metal. It operates in very high temperatures. And so if you position platinum directly on silicon carbide, unfortunately your contact resistance changes as you go from room temperature up to 600 degrees C due to generation of platinum silicides. However, if you position a graphite layer in between the platinum and the silicon carbide, you can inhibit this chemical response. So graphene, we can graphitize the silicon carbide, put platinum on top, and when you heat it up from room temperature up to 600 degrees C, you get a stable contact resistance. So there's no electrical change in the material from room temperature up to 600 degrees C. So what about electronics? So you have sensors, you have robust metallization. We need to process the signals coming from the sensors with electronics. We may need to amplify those signals, for example. This is a cross-section of a silicon carbide transistor. This is showing ion implantation of the source, gate, and drain regions, metallization, and insulating materials. We can take those individual transistors and make very, very simple circuits, such as amplifiers. This is an IV response of an individual transistor going from room temperature up to 600 degrees C. So again, this is an electronic component operating at 600 degrees C that we can then eventually integrate with our sensor devices. So what about energy harvesting, or energy, right? We need to power these sensors somehow. Our batteries don't operate at temperatures as high as 600 degrees C. So how are we going to power these devices if we want to put them inside of industrial gas turbines, for example? So what's interesting in the gas turbine is as these blades are passing each other, there's an impulse that is imparted on the surface of the blade. So you have this fluid flow, and so you have these pressure pulses that are exhibiting on the surface of the blade. And imagine putting an energy harvester there that can harness the energy from the pressure pulses. This may be a microscale device that has a release diaphragm that is sensitive to pressure pulses. And as the blade passes, there's this pulsation of pressure that's imparted on the surface of the diaphragm. If I put piezoelectric materials on the diaphragm, such as aluminum nitride, as the diaphragm stretches, I can generate a voltage. So that's how I convert the mechanical power from inside of the industrial gas turbine to electrical power that can then be used to energize our sensors or electronics. This is a graphical image of an aluminum nitride and silicon carbide energy harvester. This is a backside view of the diaphragm. Again, this is using microfabrication processes to make this device. This is the average power versus the load resistance for a diaphragm that is subjected to pressure pulses at 1 kilohertz. This is approximately the frequency that you would find in an industrial gas turbine. The blue curve here is showing the pressure pulsation at 0.46 psi, and we're able to obtain a little over 20 nanowatts of power for this given frequency and pressure pulsation. So you may be thinking that's a very low number, right? Nanowatts of power is probably not enough for your sensors. Sensors typically need microwatts of power. So if I can couple this energy harvester to a high temperature supercapacitor, for example, I can then feed that power to sensors and our electronics, and possibly even duty cycle our sensors or our data collection to minimize the amount of power that's needed. So once I have my sensors and electronics, I can put them together to make very simple wireless telemetry circuits. This is an image of a silicon carbide pressure sensor, an off-the-shelf commercially available transistor, and then also capacitors and resistors that are used to make this coal pit circuit. And this is a ceramic board and an antenna that is used to transmit the data from the pressure sensor. And this was heated up to 400 degrees C and was able to transmit the data coming from the pressure sensor at a distance of 1 meter. So this is a sensor node, a wireless sensor node operating at 400 degrees C. Imagine miniaturizing this with microfabrication processes in order to instrument the blades of gas turbines or downhole environments, for example. So I showed you a little bit about downhole applications and also industrial gas turbines. Currently, my group is starting to look at automotive applications as well. So imagine putting sensors directly within the combustion environment and understanding the pressure signatures. Also, the optical signatures of combustion environments can tell you how well that process is operating. In addition, you can put sensors at the exhaust to observe if you have complete or incomplete combustion. And again, the goal is to allow our systems to be more energy efficient, fuel flexible. Imagine combining various types of fuel and placing them inside of your combustion engine, and the sensors allow you to adjust according to the fuel that you put in the engine. And also, due to the sensors monitoring the process itself, you can have clean emissions. So currently, California is also putting regulations on automobiles, very, very stringent regulations, actually. So what this chart here is showing the LEV 3 standards, or the low emission vehicle standards. This is the third iteration of them. Again, this is by the California Air Resource Board. And so they're telling us that we cannot have automobiles with emitting particulate matter such as soot that are higher than 0.01 grams per mile by 2015, so very, very soon. So a gram of rice is 0.02 grams. So 1 grain of rice is 0.02 grams. So that means per mile that you're traveling, you can only emit half a grain of rice of soot from your automobile. And by 2028, 0.001 grams per mile. So less than a tenth of a grain of rice is what each car is allowed to emit as far as soot particulates. So what about NMOG, which are non-methane organic gases, and nitrous oxides? These also are reducing over the years due to regulation by the California Air Resource Board. So they're demanding that there's a 73% reduction in these types of gases over the next 15 years. Same with CO levels. These are not changing too much. I just pulled these values from the website, but already these are at very, very low values. So for CO emissions, we're looking at 1 to 4.2 grams per mile. So very, very low levels. So can sensors play a role in allowing our automobiles to operate with low emissions? So imagine this is actually the drivetrain of an automobile. You have your combustion engine here. Imagine placing sensors directly within the engine manifold, or placing high-temperature chemical sensors to monitor oxygen concentration or CO concentration, providing feedback to your catalytic converter or your particulate filters. And also having soot-particulate sensors that can tell you how well your filters are working or how much soot is actually being emitted from your automobile. So my group is starting to look at other material platforms to make such sensors. So I told you a lot about silicon carbide. Gallium nitride is another material that is emerging as a platform for high-temperature sensors. And it's actually being developed by a variety of industries. So I'm starting to piggyback off those industries to make these high-temperature sensors. So gallium nitride is currently being used in high-power electronics, LEDs, and I'm starting to look at sensing devices. Some of the highest efficiency solar cells are made from gallium nitride. Also resonating technology and communications, and also nanostructures. So imagine having nanostructure type sensors to improve the sensitivity of some of your devices. Gallium nitride is an interesting material platform because it exhibits multifunctional properties. It's actually piezoelectric, piezoresistive, and pyroelectric. So piezoelectric means when I stretch this material, it generates a voltage. Piezoresistive means when I stretch the material, there's a change in the resistance, which is useful in sensing applications. Pyroelectric means when I change the temperature of the material, a voltage is generated as well. So we can convert mechanical and temperature signatures to electrical signatures that can be processed with electronics. And this is useful in the design of a multitude of sensors such as bolometers, pressure sensors, accelerometers, vibration sensors, photodetectors, and gas sensors. What's interesting about gallium nitride is that you can make interesting heterostructures, such as if you put together the AlGaN or aluminum gallium nitride variant on top of gallium nitride, polarization effects and piezoelectric effects actually induce a charge at this interface. And this charge is sensitive to mechanical strains, and also, consequently, a surface charge is exhibited on the surface of the AlGaN, which causes the surface of this structure to be very sensitive to ions. And so we can leverage these phenomena to create sensing devices. For example, we can use the structure to make soot-particulate sensors. So I have researchers currently looking at small-scale sensors that can be used for onboard diagnostic systems of automobiles. Again, using this heterostructure here, when we have charged particles attaching to the surface of the structure, we can get a change in the IV response. It's basically a transistor that's very sensitive to chemical or charge at the surface. And we can package this device up and place it inside of the exhaust after particulate filtering and feed that information back to our combustion control modules. In addition, we can make other types of chemical sensors, such as hydrogen sensors, CO2, CO, or NOx. If we position catalytic materials on the gate of this transistor, these catalytic materials essentially crack or decompose the chemicals, and then we have surface ions at this interface, and we can correlate the concentration of those chemicals to the output of the sensor. So we're converting chemical signatures into electrical signatures. And again, we can package these structures and place them in the exhaust of automobiles, again, to monitor the chemical signatures coming from your combustion engine. Pressure is another measurand that my group is looking at. So can we put this pressure sensor directly within the combustion chamber itself and monitor in real time the pressure at which combustion is occurring? This is a pressure-sensitive diaphragm. As we apply pressure on it, again, this two-dimensional electron gas, or the interface of this heterostructure, will stretch, and we can get a change in the IV characteristics. What I've shown you before is a variety of sensors that all leverage the gallium nitride heterostructure. I showed you soot-particulate sensors, chemical sensors, and pressure sensors. Can we integrate all these devices on a single chip in order to make a multifunctional sensor node that is at a very, very small scale? So we can have transistors, a variety of sensors, pressure, chemical concentration, and also energy harvesters all on the same chip. So imagine having this wireless sensor node that would have a very small footprint. We're talking about 3 millimeters by 3 millimeters in size. These can be integrated inside of the walls of your combustion chamber, for example. And this type of sensor node, whether it's wireless or not wireless, can be used to collect data within these types of environments. So coming back to some of the energy systems that I talked about earlier, subsurface environments, geothermal, oil and gas exploration, and also some combustion systems such as industrial gas turbines, automotive engines, and aircraft engines. So we can design this heterostructure in order to collect a multitude of data that can then be fed back to control circuits, or also be fed back to circuitry that tells us about the state of health of these components as well. So some of the technical challenges ahead, I told you a little bit about some sensing devices, electronics. How do we actually integrate these types of devices with the systems I've shown you? So sensor placement is critical to the success of these types of sensing devices. So where do we attach them? how do we embed them within the components, and also how do we configure them within the system. So these are some of the questions that lie ahead. And also communication. I showed you a little bit about how we can make these types of devices wireless. So once we have a wireless sensor node, can we couple hundreds of sensor nodes together to create an ad hoc system, for example? So leveraging a smart dust type of system. Or we may use fiber optic cables or electrical cables in order to interconnect to the sensors. Something to think about is signal attenuation. So in a lot of these environments I showed you are very hot, chemically corrosive. Can we actually transfer that data from the sensors wirelessly? So sometimes we may encounter signal attenuation, and that's something to consider in the design of these sensor nodes. And also power. I showed you a little bit about energy harvesting, but that was for an industrial gas turbine scenario where vibration is available, but you may be in a scenario where vibration or pressure pulse harvesting is not available to you. So can we make batteries high temperature, for example? And so something we're thinking about is radioactive isotopes that can be used and coupled to these wide bandgap materials in order to make very robust batteries, and also high temperature supercapacitors. So this concludes my talk. What I've shown you is a platform material that can be used to extend the operation of sensors and electronics to harsh environments. I told you about silicon carbide and also gallium nitride, which are wide bandgap materials that can be used to make these sensor components. And then also harsh environment sensors can be used to provide data about prohibitive environments. So they can illuminate the properties such as pressure, temperature, gas content of combustion processes, which are often pollute our environment, and also tell us information about subsurface conditions found in geothermal or oil and gas reservoirs. Also, these sensors can be used to provide data about the structural health of critical components. In particular, in the oil and gas industry, it's very important to understand the state of health of those components to prevent any catastrophic failures that may damage the environment. Also, these sensors can provide real-time feedback to control modules. One thing I showed you as well is that these special materials such as gallium nitride can be leveraged to make a multitude of devices on a single chip. So we can make pressure, temperature, electronics, and energy harvesters all on a single chip. We can integrate them together to make sensing nodes to collect data in all sorts of environments. And again, leveraging the high temperature stability of these materials to collect data in prohibitive environments in particular. But of course, we need to develop standardized fabrication processes in order to realize some of those systems. So this concludes my talk. I'd like to acknowledge my former group on the other side of the bay at UC Berkeley prior to coming to Stanford. Also collaborators at Case Western University who've helped to work on the electronics side of things. And also my group here at Stanford that's starting to look at gallium nitride sensing devices. So that concludes my talk. Thank you.
Okay, so we have time for questions, and we start with the students. So any of students who have questions, go ahead. Yeah.
You mentioned a little bit in your talk earlier that getting the signal out would be a problem. If you're in a gas turbine, do you have a sense of what kind of signal strength or power of the signal that you need to get out of the turbine? And is it metal? Is it like a Faraday cage? I don't know.
Right, exactly. So inside of the gas turbine, you have to be strategic about where you place the sensor. So you don't want to cross metal, for example. But in gas turbine, there's actually what they call the gas path at the tip of the blade. So that would have combustion processes and a little bit of airflow there. So that might be a place where you would put the sensors. So at the tip of the blade and then communicating across to the housing of the gas turbine, for example.
Okay, more questions? Yeah, okay, go ahead.
A couple of questions. One is with regards to the ability to adhere silicon nitride cell devices to different kinds of substrates. There's lots of issues with certain kinds of metallizations and certain kinds of coatings. And the other is in relation to this with highly enriched oxygen environments like you might have in, say, a liquid fuel booster rocket engine.
Mm-hmm. Right, exactly. So integration, I mentioned, some of the future work for this technology is how do you embed and integrate in the platform that you're interested in. So with rocket boosters, I'm not too familiar with that technology, but for industrial gas turbines, for example, you have these coatings available to you. So can you use and leverage those coatings that already survive the environment in order to integrate the sensors? So that is something that has to be looked at. It's going to be case by case and what's available to you.
Well, silicon nitride, you can use a lot of ceramic adhesives quite nicely, but in certain shock environments or ones that are thermally dissipative, they don't react particularly well to break down.
So brittle, you're talking about brittle materials.
And also in the case of an inside of an oxygen-rich nozzle in particular, you have a film coating there that sometimes has problems with erosion that can be accelerated by some of the compounds that are insulated.
Right. So I'm not really familiar with that, but I think, I'm not familiar with that particular technology, but the bonding, for example, so how you mount the sensor and what material you use would have to be studied. Yeah.
Okay, more questions? Yeah. I've got one for you, and then Will. Okay, well, you go first, then I'll ask one. Yeah.
Sure. Debbie, I have a question. It's fascinating to see the gallium nitride heterostructure for chemical sensing applications. How stable is a gallium nitride or a component or version directly to oxidizing the atmosphere, like in an engine, for example, in a fuel leak situation?
Right. So gallium nitride is stable up to 600 degrees C in hot oxidizing environments. So it's not as robust as silicon carbide. So carbide can go up to 1,000 degrees C. The gallium nitride, you're going to have to work at moderately lower temperatures. But I'm interested in the transduction platform and the integration with this heterostructure. Yeah.
Okay, yeah, how about back there? Yeah.
I have a question, maybe somewhat naive. From what I understood here, that you are creating layers of materials with different, say, properties, right? Response to the signals, right? And then you, based on the physics, how the say, conductivity, so everything else changes in response to pressure, temperature, and so on, right?
Right.
You measure those signals, right? So the question is this design process, how you come up with those structures? Do you take maybe ready solution and just put it on new materials, or if I, for example, ask you to measure, say, velocity, I have a well which is, say, on the gas lead, for example, they're injecting the gas, and I want to measure where the gas enters the well, and I want to measure velocity, flow rate.
Okay, flow, yeah.
What would be your thought process to coming up with, say, and again, it's a harsh environment.
Yeah.
What would be your thought process, how you design the circuitry, if you will?
Sure. So for flow rate, you can use delta P, for example. So you can use low temperature technology for inspiration, right? So there are flow-based sensors in healthcare applications made of silicon, which are not suitable for high temperature environments. But there's already an electronic platform and a sensor platform in order to do that at low temperature. So that needs to be translated to high temperatures in order to operate in those conditions that you're looking at. But also the electronics have to be thought of as well, right? So you're using different types of transistors, not CMOS transistors. So your circuits are going to look different as well. Yeah.
So in other words, you're taking basically ready solutions that have been elsewhere, and you're just transforming into the new materials,
That's
right?
right. So we leverage these wide bandgap materials. We must look at the low temperature technology, but we're translating to these ceramic platforms and understanding how those materials transduce, which are a little bit different from silicon, right? Sometimes they're better, sometimes they're worse, but you have to redesign those sensing elements based on the new material platform.
Okay, yeah, back there.
Once you have a soot sensor, for instance, for a car, how would you use it? How does that change the whole car for me now? How do I drive differently because I have a soot sensor back there?
You may not drive differently physically, yeah.
My system, my car.
Yeah. What would happen? So right now, when you go for your smog check, you take a look and you make sure your engine is, for example, up to spec, or your car itself is up to spec. So you may have to change your particulate filter or your catalytic converter. So what these sensors can do is let you know ahead of time whether or not your engine is to spec. And also in the future, if you use that data in the right way, you can actually adjust your valve timing, for example, and also the air-to-fuel ratio. So you can adjust those measurements on the fly based on the sensing data. Does that make sense?
Good, yeah, you had a question there, yeah?
Yeah, so these sensors, so they'd be used in lieu of the, like we call the spaghetti soup. I would imagine in the future, but in the beginning would be in conjunction with, just so you could, make sure that they're working
Yeah,
properly.
I think the spaghetti soup would be great for calibration, actually, to verify that the sensors and the data matches what's currently used.
So my question is, then how many sensors would you think on, say, like a gas turbine would you need?
So they would love just one sensor per blade, right? So any information on the blade is value. I told you how much it costs to open up those sensors, the gas turbine, and also the gains in emissions. So any data to them is very, very valuable. So I think the benefit is the real-time data and having it all the time, 24/7, as opposed to every 3 months, for example.
Okay, we had one back there, yeah.
So I was wondering, so you talked a little bit about, with regards to automotive applications, about, how these sensors could be used in the exhaust stream, for example, right? But with regards to in-cylinder sensing, I know that, we have lots of commercial pressure sensors, but there's really nothing with regards to in-cylinder temperature sensing. Mm-hmm. So is that something you see coming in the future? Like what's the sort of technical
Absolutely. I think
path for?
Yes, for combustion, I think it's going to be a variety of measurements, and I sort of alluded to that with the multi-sensor node. So the more information you have about the process, the better you'll understand the process. So combustion is not an easy thing to understand, right? There are theoreticians that spend their whole lives understanding combustion processes. So I think it's going to be a combination of pressure, temperature, gas concentration, and possibly optical signatures as well. So clean burning flames emit particular optical signatures, and so these types of sensors can be used to monitor those in real time as well.
Okay, well, I've got one for you. So how long are we from, testing of these kind of components in real engines or real applications or geothermal wells or in oil field applications?
I think it's getting there. What I've showed you is a body of work that is around 8 years in the making, right? So these are new materials. Again, they're not as mature as silicon, so we're catching up to silicon. So we've already demonstrated these sensors at 600 degrees C, electronics. I think now it's a matter of packaging them together and interfacing them with the environment. We've done a lot of that experimentally, but not in the field yet, so that's something I envision doing in the future as well.
So do you have industry partners who are sort of waiting
Absolutely.
for these sensors?
Yeah, I do, yes.
Okay.
I do, yes.
Yeah, another question, yeah.
Can you make a comment as to how the temperatures that you've had up there for the different areas, sectors, where is that in terms of what the refinery industry uses right now to comply with environmental regulations on, say, the top of their stacks or anywhere their emissions are coming from?
So these actual temperatures are the minimum sensing temperatures that the industry would want, that they would like to have. right? So, for example, in geothermal, this is the critical point of water. 600 degrees C is a particular portion in the combustion system and the compressor blade. So they would love to have 1,000 degrees C or higher, but that's not feasible with some of these sensing devices. So this is the minimum temperature that they would like to sense at.
How far beyond that wish list is it from like what maybe they're using right now for compliance in refineries in the Gulf Coast?
As far as, so for oil and gas
Yeah.
industry, I'm not sure. I'm imagining they're much, much lower temperatures than this, yeah. Or often what they do is take data for short periods of time. So you would stick a probe down there for a few hours and then take it out before it fails, and also package it with cooling systems, so they're very bulky in order just to take these data for short amounts of time. Yeah.
Okay, well, if that's it, please join me in thanking Dr. Senesky. Thank you.
For more, please visit us at stanford.edu.